the recording, and then we'll begin. Okay, so it looks like it's now recording. So before we get into the details of the new material, or continuing on with the material that we have, I wanted to just let everyone know an update. There should now be a reading quiz regarding the introduction to combustion. So at the end of today, you'll be able to address the main parts of that because we're just getting into combustion, so it's the beginning portion of the chapter. So you will have the reading quiz. You'll have all weekend. I think I said it due on Monday, so that way you don't have to worry about trying to do something on the weekend. If you want to have it, just work on it on Monday. It's there. It's 4 questions. So just make sure that you do address the reading quiz. Secondly, I wanted to point out that there is a homework assignment for combustion, but I've just put in the introduction portion, which is what we're covering, into the energy portion, combined all of that. And so that's one homework assignment. It won't be due next week, but the following week. So do take a little bit of time, start chipping away at the pieces that you can, maybe over the weekend. And then when we get into energy, then it's not going to feel like such a long assignment, because there's combustion problems do take a little bit of time. They are going to be a little bit more tedious, is what we'll see. We do have to pay attention to very fine details. So start early. Try and get the parts of the homework assignment done early. That way you don't feel overwhelmed trying to rush through the assignment. Okay. Otherwise, let's go ahead and continue where we left off in yesterday's. Yeah, so my plan is to try and get, for the question here is the second lab. My plan is to try and get those graded this weekend and get those back to you probably by Sunday. That way you'll have them for before the third lab is due. So that is you should be getting those back hopefully this weekend for the lab reports. Otherwise, moving forward with the material that we were working on yesterday in class, we finished up the stoichiometric reactions. And so we set up our stoichiometric balance for a hydrocarbon. We worked through all the details. And one of the last things that we talked about was that when we did this perfect stoichiometric balance, it was going to represent the minimum amount of air. And so if we want to go ahead and push forward, one of the most important metrics that we're going to talk about with combustion is now going to be finding how much air to fuel do we need. And so we have to figure out what that balance is. And so in terms of the key metric that we're going to talk about, we're going to talk about the air to fuel ratio. And so this just tells us if we put in so much fuel, how much air do we need to balance this out with so that we have complete combustion. And so this is going to be coming out of the stoichiometric balance that we've done. And so in terms of the air to fuel ratio, we're going to call this value by AF, standing for air to fuel ratio. So it's important to note that if the A comes first, that means that we're going to do air to fuel ratio. And we're going to do this ratio on a mass basis. So we're going to set this up. It's going to be the mass of the air that we have over the mass of the fuel that we have to put in. Now, what we're going to note is if we do it on a per mass basis, this would be the same thing if we are doing an open system with flow rates of the mass flow rate of the air over the mass flow rate of the fuel. So these are the same things. Now, if we recall getting this mass ratio, that's great. It works for us as engineers, but in terms of our stoichiometric balance, we did everything in terms of moles. And so everything is on the molar basis, so we have to convert moles to mass. Unfortunately, we remember that a mass is just going to equal the number of moles times the molecular weight. And so we can substitute in here, and we'll get the number of moles of air times now the molecular weight of air, divided by now the number of moles of the fuel times the molecular weight of the fuel. And so we'll have this ratio. Now this works, but we want to do this in terms of what we've developed in that stoichiometric balance. And so in terms of the stoichiometric balance, what we did is we said we solved it for 1 kmol of fuel. So when we did the balance, everything was set up. And then if we solve that with 1 kmol of fuel, that means the air that we'll have is just going to be related to our stoichiometric coefficients. And so that makes it really nice. And so bringing this together, I'm just going to go ahead and rewrite it down here. Our air to fuel ratio in terms of what we know from the stoichiometric balance, it's going to be in the numerator, it's going to be the air. And so in terms of the air multiplied by the molecular weights, we're going to have A times the molecular weight of O2 plus the 3.76 times the molecular weight of the nitrogen. And then we are going to divide now by 1 kmol. So we'll just include this in here, 1 kmol of our fuel, and then we just need the molecular weight of the fuel. And so this ends up working out pretty well for us. We said, well, stoichiometric balance will basically let us now calculate this air to fuel ratio, because we said, well, when we did the balance, the A coefficient just depended on the chemical composition of the fuel, and then we can just use the molecular weights now to find what that is in terms of a mass ratio. And so that is exactly what we've done here. Now, it also could be done in terms of a molar air to fuel ratio, which we would indicate with a bar. In terms of this would just be the number of moles of the air over the number of moles of the fuel. And so that was a little bit more simple setup, but if we wanted to come up with a relationship between the two, it just becomes that we have the air to fuel ratio in mass terms would be the molar air to fuel ratio times now the molecular weight of air divided by the molecular weight of the fuel. And so we could convert between the two of them. Okay, so that is the term that we want to use. This is kind of the key terminology that we are going to see quite often. And so we'd expect the air to fuel ratio, we'd expect the air side to be much greater than the fuel, because the oxygen that we're using as an oxidizer, that's only a small fraction of the total air. So we're bringing in quite a bit of nitrogen in this reaction, so we expect an air fuel ratio to be generally not quite large. We expect it to be 20 is not an unreasonable number. So you want to bring in a lot more air than you're going to be bringing in fuel. So that is expected because of the nitrogen. So that is something that we want to note, because it's not going to be a small value. Okay. Now, in terms of actual combustion, well, what we expect is that our air is actually going to be more than just this stoichiometric value. So the stoichiometric values that we've put in this equation, well, that was assuming that the amount of air was related to A, and we said this A represents the minimum amount of air that we could add. And so if we added any less, we won't have complete combustion. But we said, well, if we don't have complete combustion, we're wasting fuel. And so it's usually a little bit better to make sure that we have complete combustion. So we generally want to bring in excess air. So we want to bring in more air than is needed. So we just have extra air. And so if we have more air in the reaction, what happens is then we still have the same combustion, but we're going to have oxygen as a product. And so that's something that we're going to see that we want to address. So we want to bring in sometimes more air and get oxygen as a product, just to make sure that we're using all of the heat, all of the energy that's in our fuel. Now, to address this, we're going to come up with a new term, and that new term is called the percent of theoretical air. And so the percent of theoretical air, by definition, this is going to represent the mass of the air, or mass flow rate of the air, divided by what we're going to say is the minimum amount of air. Now, in terms of the minimum amount of air, we're going to call this the stoichiometric condition. And so the stoichiometric condition is what we were using before. And so we're going to adjust the amount of air we actually used based on the stoichiometric value. And just because we technically call this percent, we always have to multiply by 100 to get that into a percent. And so we would expect this value to be much greater than 1. And so we'll note that if this percent theoretical error is greater than 100%, this means that we have extra air. We can have complete combustion. And so this is what we want. We want to put in a little extra air. Air is basically free. We're not paying for it. So if we have a little bit extra, that's fine, because now we're ensuring we're using all of the fuel that we've paid for. Now, in terms of the percent theoretical error, if this is going to equal 100%, this is our stoichiometric condition. So this was the balance that we did yesterday. This is perfectly balanced minimum amount of air. So we could call this the minimum air condition. And that's not air conditioning like in psychometrics. This is just the minimum air that we could bring in the reaction. Now, if this value is less than 100%, then it's going to be incomplete combustion. And technically we can't really do this, so our analysis would change completely, because in incomplete combustion we would start to see carbon, we'd see some hydrogen, we'd see some carbon monoxide, we'd see some unburnt fuel particles in the products. So we wouldn't be able to use our same setup that we had for a stoichiometric setup, because now we have a whole bunch of different stuff coming out. We don't want to get into this. So we aren't going to focus on this incomplete combustion in our analysis. We're going to try and design it so that we've had that complete combustion and we have extra air. And so this is what we want to note. This is the setup. Now, I do want to point out one other thing. So we're going to have to change the definition a little bit later for the air-to-fuel ratio for the non-stoichiometric condition. But what we'll note here is that this air-to-fuel ratio is for the stoichiometric condition in our system. So this will be the value that we will use as that 100% theoretical air that will give us our kind of our minimum air-to-fuel ratio that we will do. And so we'll note that air-to-fuel ratio stoic is going to be our minimum. And so with the percent theoretical air, this means that the actual air-to-fuel ratios that we're going to do, we're going to see larger air-to-fuel ratios later on when we get to that part. Now, I do want to introduce one more term before we get into kind of showing the stoichiometric balance for excess air, and that is the last kind of term, and it's pretty similar to our idea of percent theoretical air, and this is what we're going to call the equivalence ratio. Now, the equivalence ratio is going to be denoted by phi. Now, phi is going to be a little bit different, and so what we're going to do here is, instead of doing the mass of the air per mass of the fuel, we're going to do the opposite. We're going to deal with the fuel to air ratio, which would be the mass of the fuel divided by the mass of the amount of air. And so what we're going to take is we'll take the actual fuel to air ratio over the stoichiometric fuel to air ratio. And so again, this value will represent the minimum amount of air, which means we have the smallest amount of air, which means we'll have a smaller value in the denominator. So the fuel to air ratio for the stoichiometric condition will be larger than we would expect the fuel to air ratio for our actual condition if we're bringing in excess air. And so what that means is, if this value is less than 1, then that means we're going to be running what we refer to as a lean mixture. which means we have extra air. And if this value is now greater than 1, this means that we're going to be running a rich mixture. And we have extra fuel. And in this case, that extra fuel that we're pushing through isn't going to get fully combusted. We're basically paying for fuel that we're not using. Probably not the best choice, but we can do it. And so this was the equivalence ratio, which is one of the other metrics that we can use. Now, for the most part, in homework problems, exams, etc., our textbook really likes to kind of push more towards the percent theoretical error because it works better in terms of the equations, which we'll actually see here in the next slides. So these are going to be the terms. We've seen that we now are going to adjust the amount of air, so we have more air than is needed. And so we have to come back and try and address that now with our setup. And so this is going to be bringing in the excess air. And so this means that our percent theory air is going to be greater than 100%. And so extra air is in our system. And so this is the key thing to note. And so what we want to do is we want to now adjust the stoichiometric balance so that we can deal with extra air. So we have to go back to the drawing board. We still want to do this per unit of dry air fuel that we have coming in. So we'll do this again for our hydrocarbon fuel. This is going to be CY, and then we'll have H to the Z. We now are going to add in our air. I'm going to leave a little bit of a gap here. Actually, I'll just go ahead and put it in. We now are going to have some multiplier. We'll call that X, which is going to multiply the amount of air that we're bringing in. So we now bring in extra. And so we'll have that out front. And then we'll have O2 plus the 3.76 times the nitrogen. This then gives us our byproducts of combustion. So B times H2O plus C times CO2 for our carbon dioxide. And now we're going to have our nitrogen. So we'll go ahead and leave it here, D times nitrogen. But now, like we mentioned on the previous slide, we're going to have some oxygen that didn't go through combustion. So we have E plus O2 as a product. And so what we're going to note is this multiplier X right here. This is going to be based on the percent theory value. And so technically what we'll note is X in this case will be our percent theory air divided by 100. And so if we had, say, like 150, which we'll see in the example. So if we had 150% theoretical air, this gives us a value of 1.5 for X. So X would equal 1.5. And so we could say we have 50% excess extra air, or the multiplier here would be 1.5. So hopefully that makes sense. So this value X is going to be tied to our percent theoretical air. We just need it in terms of the setup. Now we're going to first have completed the base stoichiometric setup. And so in the base stoichiometric setup, which we did before, you would have been able to solve for the coefficients A, B, C, D. You wouldn't have E in this case, but you would have kind of already gotten a little bit started. And so if we went ahead and did our element by element balance, starting with carbon, we see that carbon will have one carbon still on the left-hand side. We'll have the carbon in the CO2. So in this case, Y will equal C. So it's the same setup as before. Repeating this now for hydrogen. Hydrogen, we just have the component in the fuel. So we have Z. We still have just the component in the water. So we have 2B. So we'll note that B is still going to equal Z divided by 2. In terms of the nitrogen. So nitrogen, we'll do this. Well, nitrogen, we now have 3.76 times 2 times A times X. So AX times 2 times 3.76. And over here we have 2 times D because we had 2 nitrogen. And so we'll end up seeing is D will just equal A times X times the 3.76. And so that just scales directly with our multiplier. And so A again was found from the previous part. And now if we go ahead and do the balance on the oxygen, well, we have 2 times A times X on the left-hand side. This is going to equal B plus 2C plus, now we'll have 2 in part E. And so we have all of these setups. And so what we'll end up being able to show is that for part E, this is going to equal AX minus 1 is the ultimate setup that we'll show. And so what this means is that in terms of the amount of oxygen, that will just be whatever we have beyond the X value. So we can just scale that up. And then that is the amount of oxygen we'll have remaining. And so again, this is just adjusting the stoichiometric balance that we had for the amount of extra oxygen that we now bring through. Okay. And so at this point, we know we're going to have extra oxygen and we should have complete combustion. However, we want to note that we don't want to overdo the amount of extra air. We want enough to ensure that we have complete combustion. But if we add too much air, then we're starting to increase the mass in our system, which means that we're going to spend more energy heating that mass up. Maybe won't get as hot of air or kind of products as we come out. And so we do want to try and keep in track of kind of thinking in terms of the energy that's going to be released, that we would have that. Yeah, so there'd be a 2E here as well. Yeah, that's where the things canceled out. And so one thing to just keep in track of, though, is that mass flow. We don't want to overdo too much extra air, but we do want enough that we keep a pretty good air to fuel ratio, such that we're making sure that we do have complete combustion. So that is the notes that I have for the air to fuel ratio and excess air. And we'll work an example of this in the later today. Okay. Now, for the last thing that we want to do is we want to note, how do we figure out in actual kind of real life situations, how much excess air did we actually have? And so we are going to be doing this in one of our labs, and you need to do this for the homework. So I'm going to point out the method that we have for dealing with extra air, and we're going to be using something called an ORSAT gas analyzer. And so the ORSAT gas analyzer is going to be able to look at the products of combustion and be able to determine whether or not we had enough air in our system. And so that's kind of the goal of this measurement. Now, in terms of the measurement, if we looked back what we needed, well, we were doing this on the molar basis. And we said, well, it's going to be really challenging to make, say, a measurement of like individual masses. So if we wanted to figure out how many individual molecules of each one of these, that's something that we don't necessarily want to do. So we have to figure out a kind of clever way of being able to figure out what are the mole values of each of these different components. And so what the ORSAT gas analyzer does is it's going to determine the molar basis of the products. And what it does is it goes back to its idea of simple gas mixtures. And what it does is it takes some of the gas and pulls it out of the flow. And then it is able to figure out what the volume of that gas is at a given pressure. And then it changes this gas sample and it measures the volume before and after. Now, if we go back in our notes, we said, well, if we did this and we kept the pressure constant, so maybe right about atmosphere, we said that the partial pressure or the partial volumes for this type of analysis, well, that could be related to the mole fraction of each of the different components. And so what we're able to do is we're going to be able to take the ORSAT gas analyzer. We're going to be able to look at what is the molar contribution of O2. And we said we're going to get that into the mole fraction of O2. And from that mole fraction, we will be able to back solve for X. And from that, we can get our percent theory of air. And so that's the exact process that we're going to do, because we're going to use this analysis technique. Now, we don't have to worry about actually doing the math on this. This is taken care of by the device itself. It will give us what the mole fraction of CO2 is, or in this case, we're going to look at it for oxygen, and we'll be able to then look at the composition of the system. And so that is the goal, and this is what we'll be doing in lab. You do need to do this on the homework, and that's why we're going to work through this. Now, in terms of this measurement, we actually have to make a special note that the amount of the mole fraction, or the mole fraction, the way it's measured, this is done on what we refer to as the dry basis. And so this dry basis is very important because it's going to change the way we approach the analysis. And so this is done for the ORSAT gas analyzer, and it's something that you do have to pay attention to. Now, what the dry basis basically means is that when it does this, we can ignore H2O. We get rid of the water vapor because that's not really good for the analysis or the analyzer. And so what this means is that if we look at the right-hand side of the stoichiometric balance, we had B times H2O plus C times CO2 plus, I'll just do D times N2 plus E now times O2. That means this dry basis is just going to be the molar contribution from these components. So this is what we mean by the dry basis. So you just ignore this component over here. And so if we go ahead and ignore that contribution, well, we need to get the mole fraction of this remaining portion of the products. And so we could say, well, we would be able to now measure the mole fraction of O2, or our oxygen. We said by definition, this would be the number of moles that we'd have of the oxygen divided by the total number of moles that we have for our products. And we'll note that this is on the dry basis. And so what this means is that we're going to have the number of moles of O2, the number of moles of CO2, then we'll have the number of moles of nitrogen, plus then we'll have the number of moles of O2. And we'll note this is always going to be for the product side, so after combustion. And so if we do this based on our stoichiometric balance, we said, well, in terms of this setup, we have a coefficient C, D, and E. And so we're going to substitute in. And so in terms of the number of moles of O2, we can use the stoichiometric coefficient E in this process. Then we have CO2. This would be C plus then number of moles D plus now E. And so we have those stoichiometric coefficients. Now what we're going to note is technically E, this would be A, X minus 1. And then for stoichiometric coefficient D, it's going to equal 3.76 times A times X. And so substituting this in one final time, we get the mole fraction of oxygen. This is going to equal, I'm going to erase this just to give us a little bit of space. this is going to equal, let's do the bottom part first. We're going to have the coefficient C, which is just determined by our fuel, plus this 3.76 times A times X, plus A X minus 1. And then in the numerator, we'll have A X minus 1. And we see that if we measure this value, we can then use this to now solve for X. Once we find our X coefficient, we can then go back and figure out what is our percent theory. And so this is the process you're going to have to use in the lab. Ninth week, this is the process that you're going to have to use on some of your homework. There is a problem that does deal with things measured in terms of the products. So that's something to keep note of. This is the setup. This is the equation that you need to use. Okay. And so that is essentially the way that we're going to deal with combustion, measuring extra air. This is how we determine whether we have a lean or if we have a rich mixture. We're able to look at what's happening in the products. And so that's the end of the PowerPoint. I did want to quickly go back here to this setup. And so now that we've talked about the extra air, if we modify this equation, the way that we're going to deal with it for the non-stoichiometric case, when we start to have extra air, is all we've done is we can now multiply this by X. So this would become AX, then we'll have the molecular weight of O2 plus now the 3.76 times the molecular weight of nitrogen divided by the molecular weight of fuel. And so I forgot to mention that. I was meaning to do that. So I just wanted to point out, now that we have extra air, we're able to include that. All we did is we modified this now by that variable X. And so we can figure that out. Okay, so that's the last thing I wanted to note in terms of combustion and our introduction metrics. And so at this point, let's go ahead and work an example problem. So we'll go ahead and pull that up. And so this example problem is based on a problem from your textbook. We modified it a little bit. And we're going to be dealing with a hydrocarbon fuel. So here we have this fuel, C8H18, and we're going to be burning with 50% excess air. So that means percent theoretical, 100% or 150%. X is going to be 1.5. We're asked to calculate the mass fraction of each of the products and the mass of the water per mass of the fuel burned. We're also asked to calculate what is the mole fraction of excess air on a dry basis, the air to fuel ratio, and the equivalence ratio. So basically, this is going to be a test of whether we can use all of the terms that we now know and work through all of the kind of combustion setup and combustion metrics. So let's go ahead and get started by writing down what we know about the system. And in this case, we know what the fuel is. It's C8H18. So this is our hydrocarbon fuel, and that we have 50% excess air. Now the excess air, we said this means that X is going to equal 1.5, because this value right here means that we have 150% theory. So 150% divided by 100 gives us that 1.5 value for X. Now, in terms of what we're asked to find in this problem, we are asked to find what is the mass fraction of each of the components in the products. We are then asked to determine what is the ratio of the water in the products over the amount of fuel that we put in on a per mass basis. We are also asked to determine what is the mole fraction of O2 on the dry basis. We are asked to determine what is the air to fuel ratio, and then we're also asked to determine what is the equivalence ratio. And so that gives us all of the things that we need to look up on this problem or find on this problem. And so in terms of getting from the known to the find, we are going to make some assumptions. And then the main assumption that we're going to deal with right now is that we are dealing with complete combustion. Now we'll get into eventually kind of talk about why we have to assume it. The complete combustion assumption just means that we're going to take all of the products, or all of the products are just going to be the ones we've talked about. Carbon dioxide, we have water, we have nitrogen, we have oxygen. We don't have any essentially individual kind of components of the fuel or any sort of incomplete process. And so that is just meaning that we can deal with it in terms of that ideal stoichiometric setup. Okay, so in terms of the assumptions, that's basically it at this point. So we can go ahead and get into the analysis for this problem. Now, the first thing that whatever we want to do when we deal with these types of problems is we're going to need a lot of molecular weights. And so let's go ahead and go to the back of the textbook, and we're going to go ahead and look up the molecular weight for all of the different components. And we'll start with the fuel, so C8H18, which is our fuel. This is going to equal 114.3231 kilogram per kmol. And then we'll need the molecular weight of the water. Molecular weight of water is going to be 18.015 kilogram per kmol. We'll need the molecular weight of carbon dioxide, CO2. This is going to equal 44.01 kilogram per kmol. And then we can deal with the other gases, so I'll need the molecular weight of nitrogen, and that is going to be 28.013 kilogram per kmol. And then we have the molecular weight of oxygen, and so that is going to be 31.999 kilogram per kmol. Okay, so those are the things that we needed to look up. Those are again found in the tables in the back of your textbook. Generally, there's some combustion tables that deal with the enthalpies of the fuel, but most of those can be found in the earlier part of the tables, dealing with the individual substances and their known properties. So again, all of those are found back of the textbook. And so at this point, what we want to do is we want to head and do the pure stoichiometric balance. And so the first thing that we want to do is we want to do this with x equaling 1. We don't want to deal with any excess air the first time through, because this will help us quickly solve for all of the coefficients. And so this is the approach that I like to take. You could do it the other way, but this helps make the later part a little bit easier. And so in terms of our stoichiometric balance, we're going to have our fuel C8H18. We are then going to have our A for air, O2, plus the 3.76 times N2. This is going to give us B times H2O, plus C times CO2, plus then D times N2. And I'll go ahead and just say D is going to be 3.76 times A times N2, because we already know that value. Okay, so now that we have that up, let's go ahead and balance the system. And so let's start with the carbon. In terms of the carbon, the left-hand side, we have 8 carbon in our fuel. On the right-hand side, we have C number of carbon in CO2. So C equals 8. And so that was pretty easy. Okay, now go ahead and move on to hydrogen. And if we do the hydrogen balance, we see we have 18 hydrogen in our fuel. And then we have 2 hydrogen in water times B. So we have 2B. And so we know that B is going to equal 9. And so there we go. We got the number of carbon. We got the number of water that we're going to have come out. So now we just need to balance the oxygen. And so balancing oxygen, we have 2 times A on the left-hand side. This is going to equal 1 times B plus 2 times C. And so dividing through, we'd have A equals B divided by 2, so 4.5 plus 2 times, or just C because we divided by 2. So then we have plus 8, so 8 plus 4.5. A gives us 12.5 for our setup. And so we can go ahead and substitute this back in. So we'd have C8H18 plus now 12.5 times O2 plus the 3.76 times N2. And then we can go ahead and say, well, then we have B times H2O. In terms of that B, that was 9, so 9H2O plus 8 CO2 plus then 3.76 times A, and so that gives us about 47 and 2. And so that would be our perfectly balanced stoichiometric system. And so that's going to help us because now we're going to redo the setup and we have to address the extra air. And so when we have the extra air, this means the X value we have is going to have that 150%. So that means we have 0.5 times more than we would before. So X is going to equal 1.5. And so that came from the setup we had before. And so again, this is where we can go ahead and make the adjustments to our equation. So now we're going to have our C8H18. And so then we can say, okay, now we can go ahead and add in A times X times now O2 plus the 3.76 times N2. This is going to give us the amount of water, so B times H2O plus C times CO2 plus D times N2. Now we're going to note that this is just a passenger, so we can say this is AX 3.76 times now N2. And now we're going to have the amount of extra air, so then this ends up being AX minus 1 O2. And so what we'd see if we did the balance, well, we know we can still show that A, this is going to equal 12.5. That's from our original setup. B remains unchanged. This is 9. C is still going to be 8. So the only thing that we've really changed is this portion of the setup. We're changing the amount of nitrogen and the amount of oxygen that we have. And so since we already know that X is equal to 1.5, we can just go ahead and multiply through. And so the result gives us the final form C8H18. And then we can go ahead and add in A being 12.5 multiplying by 1.5. We now have 18.75 out for our coefficient plus O2 plus the 3.76 times nitrogen. This now gives us B times H2O. We still said that didn't change, so that's still 9 H2O. Plus then we have C, which is 8 times CO2. And now we have to multiply the previous value by an additional half. And so we have 70.5 of nitrogen. And then we have our oxygen, which is going to be 6.25 for oxygen. And so this is going to be the balanced stoichiometric equation for the extra air. And so we're bringing through 50% extra air. Now we want to note is, again, these values for CO2 and air or water, those two didn't change. What we see is the dominating mole value we have is still going to be nitrogen. Nitrogen, because of the fact that it's so prevalent in air, is going to be absolutely massive in terms of the effect that it's going to have on the system, even though it is an inert gas. So again, this is why we keep nitrogen in this equation. Okay, so let's go ahead and continue pushing forward. We'll see how far we get. We might have to finish up this problem on Monday. And so in terms of the things that we were asked to find, we were asked to look at what was the mass fraction for each of our components. And we said the mass fraction is going to equal the mass of each individual part over the total mass. And we're going to note that we're doing this for the products. And so we have to first convert everything that we have from moles into mass. And so at this point we said, well, we can do this. Let's do this analysis for 1 kmol of fuel. So again, everything that we're going to do is we're going to basically assume that we had 1 kmol of fuel, because the stoichiometric balance that we've done is all scaled to 1 kmol of fuel. And so that means we can go ahead and calculate the mass of each individual component. So we'll just say the mass of component I. This is going to equal the number of moles of component I times the molecular weight of component I. And so we've already looked up the molecular weights. We just now need to figure out the number of moles. Now, the number of moles we're going to use, those are going to come from the stoichiometric coefficients that we just determined in the previous part. So if we were to do this for water, so H2O, this would then be the number of moles of H2O times the molecular weight of the H2O water. And what we're going to do is we're going to substitute in for the number of moles here. This would equal the coefficient B. So again, this is going to equal B times the molecular weight of H2O, where B was the stoichiometric coefficient. Now, doing all of this, we can get the mass of water. It's equal 162.135 kilograms. Now, this is a very large number because we're doing it for 1 kmol of fluid, or for fuel. So we expect this number to be large. And so that is why this value is 100 kilograms. It's just because we have a lot of fuel that we've put in. And so if we go ahead and repeat this for all of our components, we can get CO2. It's going to be 352.08 kilograms. We can get the mass of the nitrogen. This is equal to 1,974.92 kilograms. And then we can get the the mass of oxygen. It's going to equal 199.994 kilograms. And so at this point, we want to go ahead and find what is the total mass. This is just the sum of all of the individual masses. And so the total mass of this system is going to be 2,689.13 kilograms for this system. And so at this point, we can calculate the individual mass fractions. And so we have the mass fraction of water. This is equal to 0.0603. Get the mass fraction of CO2. This is equal to 0.1309. We can get the mass fraction of oxygen. It's equal to 0.0744. And then we can finish off with the mass fraction of nitrogen. So in this case, the mass fraction of nitrogen is 0.7344. And so what we find is when we've done this analysis, in terms of all of the individual components, nitrogen is almost 75% of the mass that went through the combustion process. And so it absolutely dominates in terms of mass, which is why we need to include it, because when we think of it in terms of energy, there's going to be a lot of energy associated with that mass going through combustion, and so it needs to be accounted for. And so this was just showing that value. And so we'll pick up, I think, on class on Monday. We'll finish off the last little bits of this example problem. We'll be able to calculate what the mole basis is, what the other ratios that we have, and then we'll have that complete. And then we'll start talking about the energy associated with combustion. And so that is the topic for Monday. Otherwise, this will conclude lecture today. So have a good weekend. Have a good rest of your evening, and I will see you in class on Monday.
Thank you. Have a good one.